Hi, how you doing, everyone? So, didn't quite get enough time this week to cover everything in all the classes with all the new things that we're doing. And one of the things that I did want to go over a little bit was just this idea of being able to show that 4 points are coplanar. Now, there's a few different ways that we can do this. So if we remember, whenever we have a plane, we can have 3 points to define a plane. So remember, and the way that we can then define the normal of that plane is by creating vectors from one to the other two, or actually we can take any combination and find those two vectors, and that gives us the normal to the plane. So we know that we need 3 points for a plane. And so we want to have this, we want to have a method for working out where the other plane is. And what we end up using is this scalar triple product. So the scalar triple product for 3 vectors, so it's A dot C cross product B. Let's go in order, B, C. So it's the triple scalar product. And there's a quick formula for doing this. So remember that the scalar product, has your I, J, and K here. And then if you're taking 2 vectors, so in this case the cross product is going to be B1 and B2 and B3 and C1, C2, C3. And remember that when we do this, we get like an I times something, a J times something, and a K times something. Yeah. And so if we're doing dot product of A and this, it's just going to be A times whatever this is. Sorry, A1 times whatever this is, A2 times whatever this is with the J, and A3 times whatever this is with the K. So actually, it has a very nice way of writing it. We can just replace this with our A. So it ends up just being a matrix determinant of the 3 vectors, and that will give us our cross product. So again, remember with the cross product, it gives us a vector that is at normal to the other 2 vectors, and the magnitude of this is equal to the area of the parallelogram that these vectors make. So a pretty cool thing. We get like the magnitude, parallelogram, and it's going out of the surface. And then as it happens, if we add a third kind of vector to this, so if we do dot product with this vector, and say we had another vector that was going like this, okay, so, and this we interpret as making like an oblique kind of polyhedron, just say polyhedron. So, and it turns out that taking dot product with this, and so this like height part of the vector, this one here, ends up giving the volume of the, I think we're calling them parallelopipeds or something like that. So we get the volume of that, the polyhedron. Now, how does this help us with this particular problem? Well, if these points are coplanar, so we know that 3 of them will give us that. And so if we have, let's redraw. So if we have A, and we have B, and we have C, okay, and we know that we can make these vectors, okay. If for a 4th point, so say D, we do this vector as well, and we make this our one that we're taking in combination with that dot product of the normal, which gives us the volume. So if the scalar triple product of these 3 vectors equals 0, then that means they must be coplanar. Because what that essentially means, if the first, taking the first 2, taking B and C or whatever, gives you your area of this out here, the only way that it's going to be 0 is if this parallelepiped has no height. Okay, so if it's got no height, then they're going to be 0. And so that's all we have to do. It's very nice, very easy for us. So we just take our 3, we have to define our 3 vectors first, so that will be, slightly harder than nothing at all, but we can do that. So let's just do these three vectors. So A to B, A to C, and A to D. So all coming from the same point. So A to B, let's call them U, V, and W. Yep. So let's call this U, this V, and this one W. So U is B minus A. They're just points. So U, which is going to be A to B, so it's 2, that's 1. 0 minus -1, which equals 1. And then 1 minus 2 equals -1. V, I'm going to do as D minus A. So D, A. So 5 minus 1 is 4. 4 minus -1 is 5. -2 minus 2 is -4. And W, I'm going to do as C minus A. So I'm going to have, C minus A. So 3 minus 1 is 2. 2 minus -1 is 3. 0 minus 2 is -2. So we have this. And now we just take the cross product of these. So 1, 1, -1, 4, then in the commas, 4, 5, -4, 2, 3, -2. Okay, and it's just going to end up being the matrix determinant of this. So this is going to be, so 1 times 5, -4, 3, -2, minus 1 times 4, 2, -4, -2, and then minus 1 times 4, 5, 2, 3. And we can already kind of see from the format of these that it's going to be favorable for us, but let's do it anyway. So we get 5 times -2 is -10, minus 3 times -4, so plus 12 gives us 2, minus 4 times -2 is -8, minus -8 is plus 8 is 0, and then here minus 4 times 3 is 12, minus 10 is 2, so we get 0. And so that proves what we wanted to set out to prove, that these 4 points are coplanar. So the setup takes a little bit of time, takes a little bit of reasoning in order to be able to do this. There are other ways that we could do it, right, as well. So if we took, if we have 2 vectors and we know that that gives us a normal, if we take, say, a different 2 vectors, or we do all combinations of all 3, then we could say the normals all have to be parallel, so we could do that in that way as well. But otherwise, this is nice, just simple little calculation. All right, hope you have a good week. Bye.